In the previous lecture, we have studied two modes of vibration. And now in this lecture, we are going to consider the third mode of vibration. Now in this third mode of vibration, there is a string of length L, and along that string of length L, here will be the formation of three loops. So this transfer wave is incident on a rigid wall. So crust will be reflected as a trough will be reflected as a crust. And here I am getting the three loops. In these three loops, I am getting how many nodes? Two nodes at the rigid wall. These two nodes are along the length of the string, and at the center of loop, we are getting a formation of antinodes. Clear? Means here how many loops I am getting? I am getting three loops. So length of the string is nothing but equivalent to the length of three loops. So length of three loops, so 3 into length of each loop is nothing but lambda dash by 2. So your L is nothing but 3 lambda dash by 2. Therefore, I can say lambda dash by 2 is nothing but 2L by 3. And this wavelength formula I can use in the second overtone frequency formula, that is N2. This N2 is equal to nothing but V upon lambda double dash, where V is nothing but root of T by M upon lambda double dash is nothing but 2L by 3. So now here I can say in the form as a, I write down N2 is equal to 3 divided by 2L root of T by M, which is equal to nothing but 3M. So see here, your fundamental frequency is what? Fundamental frequency N, which is equal to 1 upon 2L under root of T by M. So here for 1 upon 2L root of T by L, I can substitute here as N, and therefore this N2, which is to be called as the second overtone frequency, or it is to be called as the third harmonic frequency. So like that manner, here we have studied three modes of vibrating string. I will roughly recall all the thing again. In the first mode of vibration, I am getting one loop, therefore two nodes, one antinode will get formed. Therefore, I will get fundamental frequency N, which is equal to 1 upon 2L under root of T by M. In the second vibrating mode, I am getting here two loops. Two loops means here are three nodes, two antinodes. So your length of string is equivalent to length of two loops. So length of the string is equal to lambda dash. So I am getting first overtone frequency N1, which is equal to 1 upon 2L under root of T by M, which is equal to 2L. So this 2N is called as either first overtone frequency or it is called as the second harmonic frequency. Then in this third mode of vibration. In the third mode of vibration, how many loops I am getting? I am getting three loops. So along the length of the string, I am getting three loops. So length of the string is equivalent to 3 multiplied by length of each loop. Length of each loop is lambda double dash by 2. So I am getting lambda double dash by 2 is equal to 2L by 3. Therefore now our second overtone frequency N2, which is equal to nothing but 3 divided by 2L under root of T by M, which is equivalent to 3M. So it is 3M, that's why it is called third harmonic, and it is to be also called as a second overtone frequency. Clear? So here I am getting that your string is vibrating in three different modes, and that three different mode frequency I can say that fundamental frequency N, which is equal to 1 upon 12 root of T by n, which is called as your fundamental frequency. Then I am getting frequency n1, which is equal to 2n, which is called as a first overtone frequency, or it is called as a second harmonic frequency. And then I am getting second overtone frequency is equal to 3n, which is to be called as a second overtone frequency, or it is called as a third harmonic frequency. Right? Means your string is vibrating with frequency n, n1, n2. That frequencies I am going to write in the fashion that I can write down in the ratio format. N as to n1 as to n2 can be written as n as to 2n as to 3n, which is equivalent to n as to n1 as to n2 is equal to 1 as to 2 as to 3. Means what I can say that the string will vibrate with all integral multiple of frequency. Like your air vibration when the pipe is open at both ends. There are also air column when passes through a pipe which is open at both the ends, consists of all integral fundamental of frequency. Similarly here also, string also vibrate with all integral multiple of fundamental frequency. Now, on this particular topic, which type of questions will be there? First type of question is derive expression for fundamental frequency. How to write? First draw this diagram. From this diagram, show the node formations at the rigid support, antinode at the center. Then we can write L as the length of the string is equal to lambda by 2. From that write value of lambda, which is equal to 2L, and then put in the frequency formula. So I will get this fundamental frequency. This is first question. Second question is what about only these three diagrams? What type of question will be there? Draw neat labeled diagram showing different modes of vibration of a string. So all these three diagrams with nodes and antinodes. And then third question, which can be asked for 3 marks. The 3 mark question is here. Show that vibrating string will vibrate with all integral multiple of fundamental frequency. So here you have to show. Getting? So this is nothing but your vibration of string. Now from this vibration of string, now we are getting here as a fundamental frequency. What that fundamental frequency? Fundamental frequency n, which is equal to 1 upon 2L under root of T by n. From this fundamental frequency, now I can derive the different laws, and that laws are to be called as a laws of vibrating string. So now I can say here, from vibration produced along the string, now I can see the laws of string. For this laws of string, what I say that fundamental frequency n, which is equal to 1 upon 2L under root of T by n. What I can say first law here? Frequency n is inversely proportional to length. Means I have shown the dependence between frequency and vibrating length. I have not included the component T and M. So what I can say that tension and mass per unit length are constant. And this law is to be called as a length law of vibrating string. So this length law I can also write down in the manner NL is equal to constant, provided that T and M are constant. One more time I can write down N1 L1 is equal to N2 L2. Again, provided that tension and mass per unit length are constant. So in this three different mathematical manner, I can express your length law. And in that case of length law, if I plot a graph of frequency versus 1 upon L, then the nature of graph is a straight line. And if I plot here frequency versus L, then nature of the graph will be in this manner. Clear? So this is the graphical presentation of frequency and vibrating length. And here I am getting this as a first law. Similarly now, I can go for the second law. What that second law is there? In second law, now I am going to show the variation of frequency and tension given to the string. So what I say that frequency is directly proportional to root 3. Provided that, now which two factors I am not taken? Vibrating length and mass per unit length. So vibrating length and mass per unit length are constant. And this law is to be called as your tension law. So what that tension law? Frequency of a vibrating string is directly proportional to the tension given to the string, provided that vibrating length of the string and mass per unit length are constant. Same law I can write down, and divided by root t will always remain constant, provided that L and mass are constant. L is the vibrating length, M is the linear density or mass per unit length. And another I can say M1 divided by root of T1 is equal to N2 divided by root of T2. So on. Again condition is mass per unit length and vibrating length will remain constant. So this law is to be called as your tension. And now see here I have shown first variation in frequency and length. In second law, variation is shown in between frequency and tension imparted. Now what is the third factor remaining? Frequency and mass per unit length. So now your third law is related with your mass per unit length law. So third law is nothing but your mass per unit length law. Or it is also called as a linear density law. So what the linear density law? Frequency is inversely proportional to square root of mass per unit length, provided that vibrating length and tension will remain constant. So this is to be called as your linear density law, or it is called as a mass per unit length law. Now this same law I can bifurcate into two. From this same law I can derive two more laws. One is called as a radius law and another is to be called as a density law. Now how? See here. Small m is what? Mass per unit length. Mass is capital M is the mass of the string. Capital L is nothing but the length of the string. Or I can say small l is nothing but the length of the string. Instead of mass of the string, I can substitute rho into V upon L from the density formula. Density is equal to mass upon volume. So mass is equal to density into volume. Now this string is a wire and wire is just like a cylinder. So instead of volume I can substitute volume of wire is nothing but cross sectional area, which is equal to pi r square into length divided by length. So this length factor will get cancelled. And now what I am getting? Mass per unit length is equal to rho into pi r square. So now my mass per unit length law, now I can write down in the format. Here I can say that frequency is inversely proportional to square root of, instead of mass per unit length, now I am going to put its value. What is that? Rho pi r square. Means what? Your frequency is dependent on density Frequency is dependent on radius. Now if I want to write down radius law, what I will say that frequency is inversely proportional to R, provided that vibrating length and tension will remain constant. And if I want to show the dependence between frequency and density of material by which that wire is prepared, so I can say that law is a density law. And in that density law, what I say? Frequency is inversely proportional to the square root of R, where tension, vibrating length and tension will remain constant. And that law is to be called as your density. So like that manner, from fundamental frequency of vibrating string, frequency is equal to 1 upon 2L under root of T by M. From this formula, I can derive these different laws. So depending on that laws, what is the question? State the laws of vibrating string. So mainly there are three laws: length law, tension law and mass per unit length law. But mass per unit length law we can again bifurcate into two. That is your radius law and your density. So theoretical question is about the statement. But there are number of MCQ questions and very short answer questions will come on depending on this. Clear? So now in this vibrating string, which important formulas now we can remember? See here, I can give the listing of that formula. First, I will say that regarding vibration produced along a string, the first formula is fundamental frequency formula. Fundamental frequency formula. What is that? Frequency n is equal to 1 upon 2L under root of T by n. This is the first important thing. Second thing, what to be remembered? Vibration produced along a string will vibrate with all integral multiple of fundamental frequency. Clear? That is, I can say that P plus 1 into n. Then, third formula is, from this fundamental frequency formula, I can write down the length law. What is that? Frequency is inversely proportional to L, provided that your tension and mass per unit length are constant. Then, fourth important formula, tension law. What is that? Frequency is directly proportional to root of T.